Hey there, hackers! Welcome to Tacit Sanctuary. The Uiua language gives us really powerful algorithms, but sometimes we may have to ask ourselves, what about performance? Today we will look at two different solutions of the same problem and compare how fast they are. If you like board games, you must have heard about Scrabble. We need to combine letters to create words, and each word has a score based on the individual letters. In this exercism puzzle, we need to calculate the Scrabble score of each word. You can find many interesting approaches in the exercism solution video, but let's see how we can build this program in Uiua. While each letter has a score, some letters do have the same score, so we can organize the letters in groups. Then for the word in question, we can examine each letter and check in which group it belongs. To simplify things, let's work with the capital letters only. We can use the member function to evaluate if a letter is included in a string. Knowing the smallest score is 1 and the largest is 10, we can organize all the letters in an array of strings, which has 11 elements. The index position of each string will determine the score of the letters within. There are some empty elements, and because not all groups have the same size, we need to use the curly braces to create a boxed array. We must do this because Uiua arrays must contain elements that are the same type and shape. So encapsulating every group inside a container or box is a way around this problem. To search for a single letter in each group, we can use the inventory modifier. This helps with temporarily unboxing the alphabet array before applying the member function on each group. For example, the letter C is found in the group at index 3, so its score is 3. Okay, so we have now a data structure which represents the letter scores. How do we use it to calculate the score of an entire word? For example, we want to score the word quick. First, let's turn everything to uppercase with the absolute function. Then we can combine each letter from the word with each letter group in our scoring array. This can be done with the table modifier and giving the member function to be applied on each value pair. As a result, we get a matrix with 5 rows because we had 5 letters to score and 11 columns corresponding to the letter groups. But something is wrong here. None of the letters were found. And the reason is that the member function cannot penetrate the boundary of the box. We need to explicitly allow unboxing. And the simple way is to add another modifier called content. Now we can see one hit in every row, according to the letter positions. Q is worth 10 points, U and I worth 1, and so on. Now, how do we create scores from indices? First, we can sum up all the rows with reduce plus. This is sort of collapsing the matrix vertically. So we get a simple list showing how many letters we have with each score. From here, there is a clever Uiua trick we can use, and that is the where function. It does exactly what we need. It converts the non-zero values to indices. And also we can observe that numbers higher than 1 are getting replicated as many times as the original value. So all we need to do after this is do another sum reduction to calculate the total score. In case of the word quick, this is 20. We can also observe that the function is good with uppercase letters and still works fine if we add special characters, punctuation or spaces. They do not affect the result at all. Let's refactor the code a bit. The data structure shall be called LP, referring to letter positions. And the rest of the operations is the Scrabble by table. When scrat is invoked, first we need to put LP behind the argument on the memory stack, and we can do this with the dip modifier. Then we can run this any number of times with different words or strings. Now this is all nice and easy, and if we just want to build a toy program, then it will work just fine. However, if we care about speed, maybe because we want to score a longer piece of text, then this code should raise a few red flags. For one thing, it includes a boxed array. Boxing and unboxing always comes with some performance overhead. But even more importantly, our table algorithm is doing a Cartesian product of all possible combinations. There is no short-circuit logic. Every letter of our word is checked against every group of the LP data structure. This will cause a computational complexity of big O n times k, where k is the number of letters in the alphabet, so 26. To make this much more efficient, we need to be able to instantly look up the value of every letter. So we need a data structure that is commonly called a dictionary, or hashmap, or associative array. Luckily, we do have such a structure inside Uiua. It is created with the map function from an array of keys and a corresponding array of values. This hashmap will allow us constant time lookup, so the performance for large amount of data will be optimized to big O n, or linear complexity. Now we could take the easy way here to define our hashmap by just listing all the letters and the scores in the correct order. But where is the fun in that? To make it slightly more interesting, let's compute the hashmap from the groups of letters. Let's put the letters in a single string in order of increasing value and each group separated by a space. Now to create groups from this, we can use the partition function, which was shown in many of my other videos already. To keep the explanation simple, we copy the string, make a Boolean mask of all the letters which are not equal to white space, and then apply the box function on each partition. Then the next thing is we also want to count how many letters are in each group. So if we add here fork length, then partitioning will actually push two arrays to the stack. First the box letter group, then the letter counts. Now let's use the dip function again to push the score array behind these counts on the stack. Why do this? Because now we can replicate every score as many times as the letter count, using the keep function. Note that this is taking pairs of values from both arrays, like zipping, even without any special modifiers. So now we have the 26 scores lined up. Now let's flip the two topmost arrays on the stack so we can work with the letters. And we want to flatten this array so that it will simply contain the 26 letters we care about. We can do this easily with reuse content join, because some unboxing is needed here. Now we have all the keys and values. Finally, we can apply map to create our associative array and assign it to the global constant lm as in letter map. To retrieve the value of a letter in the map, we can use the get function. There is one caveat though. In case of unknown keys, the get function will throw an error. But luckily, there is an easy way around this. We can give a default 0 value with the fill modifier. Let's try scoring a whole word. First, we push the string to the stack. Convert it to uppercase with absolute. Then put the letter map on the stack and apply fix on it. This is increasing the dimensionality of our hashmap because we are going to want to loop through all the letters but use the same hashmap against each letter. Then we do a flip because for our get function, the hashmap must be the second on the stack. And now, ready to score each individual letter with the rows modifier and get the value by providing a default. We have an array of scores for each letter. The final step is to summarize them with reduce add. And we can create the Scram function from this as Scrabble by map. Both versions now work exactly the same way, only their performance characteristics are different. But can we actually measure the difference between the two versions? It is quite easy. First of all, we have the built-in now function that gives us the system time in seconds. And there is a shortcut to display the execution time of some code if we use under now. As we can see, the code is so fast in both cases that measuring it is not really possible. But we can try it with a bigger sample. So I selected a few verses from The Raven, a beautiful poem by Edgar Allan Poe. I put the whole text in a multi-line string that starts with the $sign characters and assign it to the name Raven. Now I can score this whole text with both functions, measuring the performance. The score is obviously the same, but as we expected, the first version is consistently much slower. If we keep running it multiple times, we see that Scrat completes in about 100 milliseconds, and Scram takes about 10 milliseconds. Hence, the performance difference is really significant, about 10 times. So that's the takeaway from this exercise. It's really worth considering if there is any way we can avoid boxing data and if we can come up with faster, better algorithms or more efficient data structures for certain tasks. In this video, we looked at two different algorithms to solve the Scrabble Score challenge, and we discovered how to compare their speed. In Uiua, often there are several vastly different ways to implement the same logic, and it may not always be trivial which one does better. There could even be certain automatic performance optimizations behind the scenes in order to mitigate some computational costs or drawbacks. So, if your code is sensitive to speed or time, it is worth analyzing it from performance perspective and look for improvement opportunities. If you found this episode interesting, then consider subscribing to the channel so you won't miss future content about Uiua, and I welcome all feedbacks or encouragement in the comment section. Thank you for watching and see you in the next one.